Well, welcome to the Austin San Antonio National Weather Service Forecast Office Advanced SKYWARN training. I'm meteorologist Aaron Treadway, and I'll be leading you through this training today. So the main thing that we're going to do is we're going to talk about a lot of different advanced topics through the guise of a specific event that happened here in South Central Texas on January 10th, 2020. We were in an enhanced risk for mainly a QLCS high wind event that day, but we did end up having some hail as well. And so we're going to kind of walk through the life of a severe weather event from the perspective of NWS forecasters. Here's the outline and some of the topics that we're going to talk about. So we're going to begin 4 to 8 days out and start looking at the global weather models, what we use as forecasters to make those forecasts, and some of the typical weather patterns and severe weather setups that we see when we're making our forecasts. As we get closer into the event, we're going to start looking at a review of severe weather ingredients and other severe weather indices, review the differences between supercells and squall lines that we cover in the basic talk. And then as we get really into the day of the event, we're going to dive into radar interpretation and spend a good chunk of this presentation looking at radar and also looking at basically QLCS or tornadoes that form in these squall lines and other aspects of the day of the event. And then we will briefly wrap up kind of tying this all back together and back to SKYWARN, looking at surveys and obviously the importance of you, the spotter, at the end of the day. So where we begin is actually with the Storm Prediction Center outlook. So these, as we cover in the basic exam, are issued all the way up to 8 days out in advance. And they currently have these basically 6 categories from no severe expected all the way up to a category of high or 5. And one of the things I wanted to point out about them is they really concentrate on coverage. So a lot of people think when they're looking at this, oh my gosh, if I'm in an enhanced or a moderate, that means there's going to be these monster tornadoes coming through the area and a massive hail. Well, that's really not at the core what these outlooks look at. They more are looking at the coverage of storms first. So for the marginal and the slight, the more common outlooks for us here in South Central Texas, they're more isolated to scattered severe weather. So we're not looking at a big widespread event like you would get as you go up in category with the more moderate and high. The enhanced is kind of in the middle of the road with numerous severe storms. We see an enhanced a couple of times a year, again, slight and marginal being the most common in South Central Texas. But I did want to bring up this quote from Patrick Marsh. He's the SPC Science Support Branch Chief, so one of the higher-ups there at the Storm Prediction Center. And he reminded us that these are generalities and that it is always possible that you could still see violent tornadoes in a marginal risk. So again, this is speaking more to coverage, not necessarily intensity when we're looking at these categories from marginal to high. Breaking it down, though, is they do have threats for SPC's outlooks for days 1 to 3 for the different hazards. So they have probabilities of wind, hail, and tornadoes. And what these probabilities are they represent the chance of a severe weather event, whatever the hazard may be, occurring within 25 miles of that point. You can actually add a layer on top of that with these hashed black areas, and those are significant areas. So that adds a 10% higher probability of a significant severe weather event happening within 25 miles of any point, again, in these shaded areas. So what is significant? Well, that's an E of 2 or greater, so getting into the stronger types of tornadoes. A thunderstorm producing a hurricane wind, which is about 74 miles an hour winds or greater, or a hail of 2 inches or larger in diameter. So we're talking more significant, worse off events. And these, again, are percentages for days 1, 2, and 3. So looking a bit more in depth at these percentages, the percent of the hazard actually drives the category. So for days 4 through 8, kind of in the out periods, longer term, they really only get a 15 or 30% chance. Just kind of these more generalized areas, but they do kind of correlate back to the slight or the enhanced risk in the days 1 through 3 outlooks. As you start getting in, again, those probabilities start to, again, coincide with the different hazards. And really in day 1 and day 2, it's the drivers of what hazard is in an area. So, for example, if across South Central Texas, they were going to say that we have a 50% chance of, wind or hail. Well, that's going to be a slight risk across our area. If it's a 15% chance of tornado, which actually rarely ever happens here in South Central Texas, that actually bumps us up to an enhanced risk. So obviously, because tornadoes are a lot more life-threatening, then hail and wind damage, lower percentages there results in higher categories at the end of the day. So while the categories do tie back in mainly to coverage, they also do relate back to chances of specific hazards as well. And let me kind of explain that in a little bit different way. So diving in even deeper. So we have a nice little supercell here. It's a nice cartoon, idealized supercell. And we're going to say that on this day, the main threats are wind and hail. We're not going to worry about tornadoes at this point. So we got a supercell out there. Well, SPC issues a marginal risk, right? So isolated severe thunderstorms possible. So you have your house and you've got one supercell out there. That's kind of the definition of isolated. And going back to those tables, you've got a 5% chance now of either wind or hail impacting any single point within 25 miles of that single point now on this marginal risk day. So you have less coverage, and so there's less overall threat. You've only got one storm, so less coverage. Again, going back to that isolated. And then you have a 95% chance that that threat doesn't occur in the 25 miles. Because remember, 5% chance that it does, 95% chance that it doesn't. So maybe that supercell moves due east, and while, hey, there was a supercell out there, somebody got wind and hail, it just didn't happen at your spot. Okay, so now we're going to ratchet it up and look at an enhanced today, okay? Going again back to the tables, now we've got a 30 to 45% chance of these wind and hail threats, okay? So now we're talking about numerous severe storms possible. So now, instead of one supercell, we've got three. And we've even got a more intense one that kind of represents that significant severe category that's represented there. So now you're kind of surrounded now with these numerous severe storms. So looking at that, now it's more coverage, so your threat is now greater overall. So this is how the categories that mainly talk about coverage relate back to the threat possibilities as well. Because if there's more coverage, your threat is now overall greater because there's more storms. So now you have a 55% chance that the threat doesn't occur within your 25 miles. So we've gone from a 95 to a 55. So the chances of it impacting you are increasing. And because of that, the chances of any of these hazards are also increasing. So in this case, one of these three supercells is probably going to impact you. So that is how, at the end of the day, the SPC outlooks relate coverage to also threat hazards as well. And two other important aspects to remember about these outlooks are they are over a broad area. So this is now an example of the outlooks from our January 2020 event, and then every single storm report that was issued. The reds are tornado reports, the blues are wind, and the green is hail. And if you notice, these are really broad, really big outlook areas, and the hazards don't, occur across every part of it. So there are parts of the outlooks where nothing happened. Between Killeen and College Station, there's actually a fairly wide swath there going up towards Waco and just east of Dallas where there were no reports. But just to the east of that and just to the west of that, there were a lot of reports. So the threat may not occur in one area of an outlook, but it may occur in another area of an outlook. And the other thing, too, is these are outlooks. These are forecasts. These are predictions out in the future and more general, more broad forecasts. These aren't observations. So we're looking at the state of the atmosphere, what the atmosphere could do, what it could produce at the end of the day with all the different indices, which we're going to talk about, all the different ingredients coming together at the end of the day. So if the atmosphere is primed for it, then, hey, they're going to issue an outlook for that area. Okay, so days 4 through 8, and specifically, again, looking at this January 10th event. Any background that you see in this presentation that is blue kind of specifically looks at details of the event, where the gray ones are more factual, more informative, just kind of general slides. So again, we're going to quickly review global weather models and some of the differences there, and then looking at the conceptual models, these ideas of severe weather events that we look at. So these are the days 6 5, and 4 outlooks from the Storm Prediction Center. Again, we're looking here in Central Texas as the main focus during this presentation. And the models really early on suggested the threat may be more East Texas up towards the Arklatex. So you can see the day 6 kind of barely clips South Central Texas. And by day 4, that threat is at least spreading a little bit closer to our area. So the models, again, the timing suggests the threat mainly East Texas because later in the day. And then they do suggest a synoptic setup close to some of these conceptual models that we'll talk about here in just a second. So in general, what are weather models? So models are basically what we run so that we don't have to do sitting in the chair every day, these very intense equations that you see in the top right. So when all of us meteorologists who are degreed meteorologists go to school, we learn how to derive these very calculus-heavy complex equations that actually govern how wind, how moisture, how different things move and change in the atmosphere. So all of these are derivatives, rates of change, very complex equations that are formed basically from some very basic science that, you know, Newton and others developed with the ideal gas law and the second law of motion. All of those equations feed into these more complex ones, again, that govern kind of things in the atmosphere. So these models do all that advanced math for us, thankfully. So models take in initial conditions, so what the current state of the both atmosphere and the surface of the Earth are. They plug all of that into these equations, and then they produce nice graphical outputs for us to look at and interpret. Typically, global models are run 4 times a day, so we're going to start off looking at models that look at weather across the globe or across wider areas. And they do have different resolutions, different inputs like initial conditions, and different little ways that they run the math. And so that's why there are differences at the end of the day at weather models. That graph there on the bottom right is actually a graph of chances of precipitation from different weather models. And as you can see, there's a wide range, especially as you go out in time. You know, some of the models saying that there's only, 20 or 30% chances of rain, while others say anywhere between 70 and 90. And that, again, is just because of those subtle differences in how they take in data and how they do the math at the end of the day. Really, the 2 big weather models that you'll probably hear talked about all the time, from news media, whether that's local, national, the Weather Channel, to us in the Weather Service, private meteorologists, anybody, are the GFS and the ECMWF. These are the 2 big weather models out there. One of them run by basically NOAA and the National Weather Service, and the other run by the European Center of Mid-Range Weather Forecasting. And these are the 2 that a lot of people look at. And really, it's a duel between the 2. Which one is better? There's a lot of discussion about, hey, which one is better at things? The ECMWF tends to be a little bit better at hurricanes. The GFS has its own advantages, too. And these are also run out to 6 to 10 days at a time. The GFS actually runs even further than that, all the way out to 16 days at times. And we only get, though, those first 10 days in our systems at the Weather Service. And that's because that second week, that additional week at the end, typically trends towards climatology, what is expected to happen for this time of year, and gets away from, a lot of those initial conditions, because we're now talking, a week and a half in the future, and a lot can change between now and that week and a half. The ECMWF again runs 10 days as well, but and so these are the 2 main models that we get and use. 2 other ones that we use are the Canadian and the UKMET. So again, these are run by different countries, by different meteorology organizations, like the Environment and Climate Center of Canada or the UKMET office. These 2 also go out to that 6 to 10 day range. So you can enjoy the little memes that I have there. But again, these are models that predict the weather and predict what different levels of the atmosphere are going to do across the globe. So in these screenshots, it's just the U.S., but all of these cover the globe. And so they allow meteorologists anywhere to use them, predict the future, and to start to compare them to each other. As we go down in resolution, we now start having the NAM and the 3-kilometer NAM. So these, again, are run by NOAA and the National Weather Service here in the United States. These are American models. And these now only go about 2.5 to 3.5 days out. So the benefits here are that the resolution is getting smaller. So instead of kind of looking at wider areas, we're now starting to get a lot more detail in these models so they can start to realize things like convection and storms, lines of storms, smaller features in the atmosphere to hopefully provide us better data. And so we look at these things and we use them, in concert with each other. What is, the NAM saying in the next 3 days? Does that compare to what the GFS, a more broad scale resolution model is saying? Okay, how does that bode for the 7-day forecast in the GFS? We're constantly comparing these models to make the forecast. And some of the other things that we do with them is we model the trends in the timing and strength of weather systems. So that's really our big thing, and that's why us as meteorologists like to look at models every single day. So here, for example, on the right side is a 4-panel that I actually have in my computer system at the office, and it's comparing basically a trough, so a low-pressure system, and a front moving across Texas. And it may be a little bit hard to see, but there are subtle differences in the timing and the strength of that low-pressure system in that front. So some have it further east, some have it further west, some have that low stronger, some have that low weaker. And using the trends and using those comparisons, both in timing and consistency from run to run of each model, we start to make our forecast. We also know that different models have different biases. Some may be wetter, some may be drier or warmer, some, especially in seasons, may be doing better than others. Really an important key, though, is we have to check how they initialized. Did what the model says at hour 0, when it started, when it basically should be taking in initial conditions, taking in what's happening right now, and spitting that right back out? Is that accurate? Because, hey, if it's accurate, then we've started off in a good place. If it's not, if that initialization is not good, well, then those errors that might already be in there may propagate through the rest of the model. And then at the end of the day, before we make any forecast, it's a mental check. Hey, is what I'm forecasting, is what this model is showing, does it make actual sense to what I have learned in college, to what I have seen actually out in the real world at the end of the day? A couple of other model features are some models are run in ensembles. So this is now the same model being run several different times. So one of those is the GFS, again, our kind of broad scale global model from the US. It's actually run with 21 different members. And it basically is a slight tweak for each one of those members to see how it changes over time. So on the right side, you can actually see each of those members, each of those lines represents one of those members. And we start looking for things like clumps of them together. So in this graphic, for example, the blue line is the mean of all of the members, where the black is actually the operational version, the version that you would find online that I would use at the end of the day. And then each of those gray lines is, again, one of those members. So you have a big clump of less than 1/10 of an inch of rain. And then you have, other little clumps, maybe one around 0.2, 0.3 there, with one member saying, hey, there's going to be about 1/2 inch of rain. And you can see the mean, see where the operational model is, and you start to, factor in uncertainty. Do some of the members say we're going to get a ton of rain? Okay, well, I've got to keep that in mind as I do the forecast. While most of them show that that's not really possible, and that's probably what I'm going to put in my forecast, maybe I'll mention, hey, there's a slight chance that we are going to get a lot more rain at the end of the day with a few of these members showing that. The other thing is that these models also look at all of the layers of the atmosphere. So on the left is an observed sounding that we release from Del Rio, showing the profile of the atmosphere, the temperature, the moisture, and the wind going up in the atmosphere. And we use that to forecast severe weather, forecast different phenomena. We look at these profiles a lot of the time in winter weather events, and the models actually produce these as well, trying to make guesses and make forecasts about what's going to be up in the atmosphere. So again, going back to those initial conditions, comparing what is real to what the models are forecasting is something really important that we do. So these are actually, I believe, for about the same time step. And again, we're trying to correlate them and see the small differences between what the model is actually saying and what was observed. The other benefit is that these models can fill in gaps between our official upper air stations. So for us here in Central Texas, we've got a station in Del Rio, and we've got a station in Corpus, and one in Fort Worth. and then the next closest stations are over in Louisiana. So there's this little gap, and these model soundings can fill that gap in. So we take all of that, all the information from the models, all of these observations, and then we start to apply conceptual models. So on the left, you see basically the idealized mid-latitude synoptic scale cyclone. Those are a bunch of fancy words for the typical low-pressure system with a cold front and a warm front, and then the upper air conditions that we need for strong to severe thunderstorms. So you have the front, you have these upper level winds, and then you start looking at the weather maps and say, hey, do we have all these conditions? Do they all line up? And on this day, again, in January, we had a cold front sweeping across Texas. Cool, check. We had a bunch of low-level moisture coming from the Gulf of Mexico, which we'll talk about here in the next couple of slides. And then we had a bunch of wind coming southwest across Mexico, across Texas to the northeast, across the Central Plains. And that's called the low-level jet and the subtropical jet all coming into Texas ahead of this front. So all of these things fit together to say, hey, we're probably going to have severe weather. Everything is lined up kind of synoptically with the fronts and the upper level winds. And then we start looking at the four main ingredients that it takes. And we learn about these a lot in the basic SKYWARN, so go check that out on YouTube or attend one of our classes for sure. But we're going to review that here and review a couple other severe weather indices and where you can find those online. So again, we've kind of started each of these days looking now at the SPC outlook and the discussions that our office and SPC have released. So now we now have all 5 of those categories out there. So we've gone from those 15 and 30%. Now all the categories, you can still see the main thread is going to be across East Texas. Houston's area, Shreveport, Lake Charles, kind of that area is the focus with that marginal kind of splitting Central Texas in half. But forecasters are already looking at these 4 ingredients, and we use these again mentally to kind of check things off and say, hey, do the ingredients for severe thunderstorms line up? So this was a discussion, and you can see in the highlighted area, moisture lift, instability, and shear were already being talked about. And that's because those are the 4 ingredients needed to produce a severe thunderstorm. So again, we have all of these a lot of the time, especially in South Central Texas spring. And so we're going to dive back in, review some of those, and talk a little bit more in depth about them. So moisture, first off, is the amount of moisture in the air. And we have a big source of that here in Texas. Kind of down to our southeast, you may have gone to a beach along it at some point. It's the Gulf of Mexico. A lot of the times we have southerly winds, and that's bringing moisture off the Gulf here into South Central Texas. So one way to do that and kind of measure how much moisture we have in the area is to track the dew point. Tracking humidity is another way to do that, and then tracking precipitable water, which we'll talk about on the next slide, is a third way as well. So when we have a ton of moisture, if lifting does occur, that's when we start to get clouds and storms. So again, precipitable water, you may hear this in our discussions or again from the news media, and it's basically the total atmospheric water vapor in a column above an area. So if you stood somewhere and took the total atmospheric moisture, the water vapor above you, that is the total precipitable water. And we actually express it in an amount. So you might hear a 1.2 inch precipitable water. And that's basically how much moisture then would fall out of that column of air at the end of the day. So obviously the higher precipitable water, the more moisture there is in the column of air above you. So we start to look at these and can actually get these values from the soundings that we release. So this is now looking at a Corpus sounding. And you can see the traces of temperature and dew points, but also we start to get a lot of these indices, and one of them says PW equals 1.14. So a 1.14 inch precipitable water, and we can actually look back in the data and see where that ranks climatologically. So for that time in early January, that's actually very close to the 75 to 90% moving average there for Corpus Christi. So that's saying that, hey, that's actually abnormally high moisture for that day coming from the Corpus area into South Central Texas. Okay, so the next thing we look at is instability, and that's really just taking a warm bubble of air and asking, will it continue to rise as long as there's warmer air as long as it is warmer than the air around it. So looking at that kind of conceptually, now we have our green blob of moist air there, and it typically goes from the warmer environment at the surface to colder aloft, right? So it's going to rise into the colder air. Well, some of the times we have a layer of warm air in the middle of the atmosphere, and that temperature inversion, or sometimes called a cap, actually prevents that from continuing to rise because, hey, now the air around it is warmer than itself, and so it is trapped there at that layer. So oftentimes you'll hear, hey, the atmosphere was primed for storms, but the cap prevented it. Again, it's keeping that air from rising. And what you need at the end of the day is a source of lift, like a front or a dry line, or some cooling to occur in the mid-levels of the atmosphere to, again, allow that bubble of air to continue to rise. We measure how much instability is in the atmosphere by something called convective available potential energy, or CAPE. So basically, for storms, the more CAPE there is, the stronger and faster an updraft in a storm can form and can thrive in. So you learn about updrafts and downdrafts again in that basic talk. Feel free to check that out. But the more CAPE there is, the more potential, especially for larger hail, for a lot more upward motion there is. So weather balloons and aircraft can measure temperature and dew points, and we use those values to calculate the amount of CAPE in the atmosphere. So going back to that Corpus sounding, again, one of the closer soundings on that day, you had 2,000 to 3,000 joules per kilogram of CAPE. That's a lot of CAPE. That's a good amount. That's going to lead to some strong to severe thunderstorms. Again, so second ingredient now is in place. And so you can pull up all of this data that I'm showing you from the Storm Prediction Center. It's freely out there for anybody to look at. One thing that is a little bit more limited is we can actually, internally in the Weather Service, unfortunately this is not an external thing, but aircraft. So your big 737s flying out of Austin, Berkshire, or San Antonio International, or even the big international flights, most of these airplanes actually track at least temperature as they ascend and descend into these airports. Some actually track moisture as well. And we can use these, again, as soundings to fill in those gaps between those more national sounding sites that I've been showing you, like Corpus and Del Rio. So again, this is internal data to us, but it updates a lot more often. So instead of twice a day or maybe 4 times a day from those full soundings from Corpus and Del Rio, planes are always taking off and landing. So we can actually see the state of the atmosphere more constantly with these. Okay, so you have plenty of moisture, you have plenty of energy built up in the atmosphere. Now you need that spark, that thing to set it off. And really, that can come from many, many different forms. The first of which is a cold front or a warm front, probably one of the most common that you would know about. A full upper level disturbance, just an area of low pressure, can actually force air upwards. The jet stream by itself, so even if there wasn't a front there or a low pressure there, if there were differences in speed that the air is moving in the upper atmosphere, it can actually be moving faster, and when air is moving out of the way, other air has to go and take its place, so air rises to take its place. Some other common are differential heating. So this happens a lot of the summertime in Texas when you have the cooler Gulf of Mexico and the warmer land across the Texas coast. This is why we get the sea breeze and sea breeze thunderstorms during the summer. Dry lines is another big feature in the spring for Texas, where you have the warm, moist air over Houston and Austin and San Antonio, and the very dry desert air across West Texas. As that dry line tries to move to the east, it actually acts like a front. And then something called orographic lifting. So that's just topography. As air moves up and over a feature, like, for example, the Edwards Plateau. You have the lower areas here along central Texas and the Texas coast. Then you have the Texas Hill Country. If you get the right conditions, you can actually have lifting that occurs as the air goes up and over topography. So again, going back to our January event, we had a cold front moving through the area, and that was our main source of lift on that day. So again, third ingredient checked off. And then the fourth ingredient, and this is the one that really allows for severe weather, is wind shear. So this is a difference in wind speed with height, either speed or directional shear. So again, you can have maybe slower winds at the surface and faster winds aloft, or you could have, say, southeast winds at the surface and northwest winds aloft, or a different direction. Those two elements of wind shear are there, and what they do is they help tilt the thunderstorm and help it last longer. So wind shear is not needed for the storms to actually develop. We only need those first three ingredients for that. But wind shear is the thing that helps prolong the life of the thunderstorm at the end of the day. Helps it become severe, helps it last a lot longer to produce all of these hazards. So what we use to observe it, most of the time is called 0 to 6 kilometer shear, or that's basically a measure of the shear in most of the atmosphere. So it's produced by most global and mesoscale models, so we can actually see how much shear is expected to be in an atmosphere ahead of time. It is on the SPC Mesoanalysis page, and really what you're looking for is about 50 to 70 knots of shear as a source of lift, like the front was approaching on that January day. So again, now we have all four ingredients in place that we've been able to see forecasting from those global models for several days. And now we're going to start getting down into the nitty-gritty. Now this is a day before. We're going to review supercells and squall lines and the different hazards that may come from both. And look now at more finer scale models called mesoscale models. And those are now looking at a higher resolution in a smaller area. Okay, so now we have a big change. This is now the day 2 severe weather outlook, and they've pushed this severe hazard further east. So now the Austin and San Antonio area are in that slight to enhanced risk, and they've actually added a moderate up near the Arklatex. So now the threat is actually looking more and more likely across our area in South Central Texas. And the conversations, the discussions are now mentioning severe threats in terms of the hazard. So it says the main threat will be damaging winds from a squall line developing over the eastern hill country and moving across the I-35 corridor. Okay, damaging winds, main threat with the squall line, but should there be any thunderstorms that form ahead of the line, any supercells, then tornadoes and hail may actually be a greater risk at that point. So if it's a squall line, it's going to be wind. If it's more isolated, have more supercells, then the tornado and the hail threat are going to be greater. So again, just a quick review of supercells. This is the idealized one of what they look like. For more on this, refer back to the basic that we have posted on YouTube. But you do have, again, the updraft and the downdraft. The updraft region is where a tornado would form as all the air goes up in that rotating updraft called a mesocyclone. The downdraft is where the heavy rainfall and the large hail and also the significant damaging winds would all come from. And so that's idealized what a supercell is. And basically, again, supercells can produce all types of severe weather, the winds, the tornadoes, and the large hail. If it's a very strong updraft, the main threat is typically large hail. The rotating mesocyclones, as I said, can produce tornadoes. And those downburst winds coming out of the downdraft are where the damaging winds come from. Contrasting that with squall lines mostly develop in a linear fashion, and they're just basically a line of storms associated often with a front or a dry line at the end of the day. Wind shear is often oriented perpendicular to the line of storms, and damaging winds tends to be the main threat when you get these linear line of storms. Supercells can develop either within these lines or near the main line, as we were just talking about on the previous slide, where they could have the supercells develop out ahead of it. And then tornadoes are also possible, and some marginal hail with these squall lines. But again, winds tend to be the main threat. That said, here in Central Texas, in the last 10 years, we have had 69 confirmed tornadoes in our county warning area, in the area that the Austin San Antonio office serves. Only 10% of those tornadoes have been associated with supercells. Typically across the Central Plains or the Southeast United States, you really get these supercells that form, and that's where a lot of these big damaging tornadoes do come from. Well, here in South Central Texas, it's more from these what are called quasi-linear convective systems, or squall lines. We can actually get little weak tornadoes out of showers. If the winds come together just right, it'll create a little spin up and actually produce a weak tornado. Multi-cell clusters and then tropical rain bands from hurricanes can also produce tornadoes here in our area. So we're not really on the lookout for these big massive supercells in our area. It's more these linear or complexes of storms that we're looking for when it comes to tornadoes. So here's an example of a tornado threat transitioning to a straight line wind threat out of the Corpus area. So you can actually look for these little hooks in the squall line, and that's the greater area for tornadoes, the greater risk for tornadoes. So that small appendage, again, kind of suggests that threat, and I'll show it to you in velocity on the next slide. And then what happened is that line, as it moved towards the Texas coast and then off the Texas coast, it actually transitioned more into a severe wind threat. So you now see that bowing section from Rockport to Port Arthur there, and that's where the heaviest straight line winds are going to be. So looking at that on velocity, this is now a measure of the winds coming out of the thunderstorms, and we're going to talk about this here in just a couple of minutes when we get into the radar section of this talk. So where you see the greens and the reds right next to each other, that's a radar couplet or a radar rotation, so a potential tornado that we see there. And then again, as it moved eastward, it's now all one direction of wind moving off the coast, and that's a large area of damaging straight line winds, again, moving towards the coast. So these things can transition in these squall lines from a potential tornado threat to, again, that main damaging wind threat. Okay, so briefly to review, squall lines mainly produce damaging winds. At times, radial velocity can be misleading because the squall line itself is moving perpendicular to the radar beam. So again, that's if the radar beam is looking out an area and the squall line moves perpendicular to it, you get some squirrely velocity values, and we'll talk about that actually later in the presentation. And squall line tornadoes usually exhibit small breaks or hooks in the line. Typically, they're a little bit weaker, but you still have to be on the lookout for those velocity couplets there. Okay, so we've talked about squall lines versus supercells, so now let's look at more convected allowing models. So these are now more high-resolution models, and they can actually resolve individual storms, where those global models tend to just show general areas of rainfall, kind of big blobs of rain at times. These convection allowing models can actually resolve each individual little storm because they're higher resolution. Again, you can either use them alone by themselves, one-on-one, or as part of an ensemble. And a lot of them produce simulated radar images. So we'll tweet out at times these simulated radar images. Again, it's what the model thinks is going to happen. It's not exactly what's going to happen, but it is the model's best guess. Two of the most common ones that we use in our office are the HRRR. You'll probably see this one a lot on television. It's, again, the US's high-resolution model. It is actually updated every hour, and it could run out to 18 hours, or every 6 hours it actually runs out every 36 hours. So, again, this is now just looking really at the next kind of day to day and a half in terms of convection, but it's doing this at a much higher resolution, at a much more detailed forecast. The other is what's called the Texas Tech WRF. So WRF models are basically models that anybody can run. You can go online and look up a WRF model, and if you have some computer programming background, actually set it up, set your own parameterizations, your own kind of rules for the model, and produce one. So Texas Tech and their atmospheric program up in Lubbock has actually set one up, and it actually does pretty well here in Texas. It's one of the more trusted ones that we kind of go to a lot, and they actually offer a Texas Tech WRF ensemble as well. The Storm Prediction Center also has their own ensemble of high-resolution models. So the HRRR is a member of that. The NSSL, or the National Severe Storms Lab, kind of our big science branch in the Weather Service, has their own WRF model. They take a high-resolution version of the NAM, which we've already talked about, and a couple other models as well, and kind of put it all together. And with that, they create an ensemble of these high-resolution models. So again, looking now within the next 1 to 2 days, and it can produce different things like chances of reflectivity, or the amount of rainfall, or again, the simulated radar. So a Storm Prediction Center uses a lot of these in their convective outlooks, in their forecasts, to kind of see what's happening now more in the shorter term. Okay, so for the January 10th event, this is what the Mesoscale models were showing. So this, again, is a common graphic that you may see put out by our office, and it steps through time with that simulated radar. So in this case, it's the HRRR, showing a couple of storms developing by 5 o'clock across the hill country, But by 7, as it moves through San Antonio and approaches Austin, you've already got a line of storms, with it kind of breaking apart a little bit and weakening as it gets later in the night. So our forecast considerations for that day, for the January 10th event, were, hey, if there were any isolated initial storms, the main threat was going to be hail. If that doesn't happen, the hail threat's a little bit less. But if there are any isolated storms, hail is the main threat. If those storms go supercellular, then any threat could be on the table, including tornadoes. But really, once those storms start to line up, the main threats are going to be damaging winds and then any potential weak tornadoes as well. Okay, here we are, the day of the event. Okay, so through this time, you know, us as forecasters, a lot of my thoughts are what we're doing and thinking about in the office, you know, leading up to an event. We're staffing up, we're getting more people, we're making these accurate forecasts, we're coordinating with SPC, we're getting the information out to our partners like emergency managers and the broadcasters to help us message it. But now we're at the day of the event. And so this is what the day one outlook looked like from the Storm Prediction Center. And again, we're providing qualifiers about the hail potential. So saying some high resolution models show the potential of isolated cells developing. If that does occur late this afternoon, large hail may be possible. But again, notice the qualifiers there of some high resolutions, you know, if that happens, should that happen. We also acknowledge that there is a QLCS, a linear tornado threat. So we're saying we can't rule out a brief tornado with this setup, and we'll model or monitor for localized, you know, bowing segments or kinks in the line of convection where those tornadoes might be. So again, the SPC has kind of moved the threats a little bit back towards South Central Texas. And through those hashed areas, they again show that the main threats are going to be the winds, but they also are accounting for that hail threat, that potential hail threat, by putting our area in that hashed severe hail look on that far right. So again, we as forecasters at the local office, we're saying, hey, we're going to qualify that hail threat of, hey, it's an if things occur in a certain way, there's going to be a lot of hail. But at least the atmosphere itself is primed to produce large hail with the steep lap swades, with a lot of that air moving up in the atmosphere. So one other thing is the morning of, I believe it was the 12Z or about 6 or 7 a.m. Update from the Storm Prediction Center, they actually mentioned a derecho. And what that is a widespread long-lived wind event associated with a squall line or QLCSs. So typically, derechos don't really happen a lot in the south or in our area. They're more kind of a Midwest thing where storms will start across the northern plains and then move across the Ohio River Valley, leaving a long swath of wind damage. Well, this was mentioned again in that morning outlook, and a lot of folks were worried about that. Like, what does that mean? Does that apply to here in Central Texas? So one of the things is you have to remember that outlooks are for a large area. So pay careful attention if you're reading one to exactly the timing and the geographic area it talks about. So you have to remember that. But then looking after the fact, looking at all the reports. So again, the blues are winds and the reds are tornadoes. And if you look from San Antonio to the Arklatex up through Arkansas towards Memphis, you actually do have a long swath of wind damage reports that actually continued all the way into the Carolinas. So, hey, does that fit the bill of a widespread long-lived wind system? Yeah, it kind of does. So what did start here in South Central Texas did kind of end up being a derecho at the end of the day. So that actually did end up fitting the bill. And so I did just want to briefly cover that. So I did want to mention our staffing, since a lot of this is not just about informing you of these different weather elements and these different resources that you can look up, but also kind of peeling back the curtain from the Weather Service and what we're doing leading up to these events. Now we are day one of the event. And so on this day, we actually had 7 forecasters in the office. So the picture here is not of the event that we're talking about. This is actually a much earlier picture from a couple of years ago, but it does generally demonstrate what the different roles in the office are. So typically you have one coordinator, someone who's just kind of in charge, making sure everybody has a job, making sure no one is overwhelmed. kind of working with everybody in the office to make sure that things are going smoothly. Then typically we have 1 or 2 warning coordinators. And so in this picture, that's the people, the 2 in the background there, looking at radar images. So they're the ones actually issuing those warnings. I'm actually in the foreground here in the red shirt, looking at Twitter. So we have one person who's running social media in NWS chat. Social media, we have Twitter, Facebook, that we're posting on a lot during these bigger severe weather events. And NWS chat is a chat service that is internal to the weather service that we use to talk to the media and talk to our emergency management partners, kind of give them a little bit of a heads up and explain a little bit more. But really the messages going out on social media and NWS chat are, mirror each other, are very close together. And then we have at least one person on the phones providing what we call decision support. If an emergency manager calls up and says, hey, I have an event, what is that thunderstorm going to do that's headed in our direction? We give them that. So you can see the person in the light blue shirts talking on the phone there with the headset. So that's what they're doing. We have another person who's trying to verify the warnings that we issue, get storm reports from you, the spotter, whether that be from social media, whether that be from phone calls. Maybe we're calling you to try to get the reports. And then we have one last person who still has to do the standard forecast that we do. We produce aviation forecasts 4 times a day for 4 airports. We have the grid package, our 7-day forecast that has to go out twice a day. And we obviously have to keep all of that updated as these storms move through. So we still have to continue to do that as well. And in bigger events, like think back to the big Memorial Day floods, the big Halloween floods here in South Central Texas, we add other people. So we may add river flood forecasters. We may split up those warning responsibilities with somebody concentrating on the hail, the wind, and the tornado threat, while others concentrate on that flash flood threat. And then we kind of rotate jobs as needed. We try to not get in a focus area. We try to not, get kind of one-track mind, but we rotate them around. And we can get as many as 12 to 15 forecasters in an office. We have 1, 2, 3, 4, 5, 6, 7 workstations that we can issue warnings from, and even more PCs than that in the office. And so we can pair up and start to really effectively use all the technology in our office. Okay, so going back to that event, leading up to the watches that were issued, we had Mesoscale discussions that came out. So usually these discussions are a little bit more technical, and they focus on the next 1 to 3 hours of what is expected to happen. So these ideally come out either right before the event saying, hey, this is a heads up, and these storms may be about to form. We may actually need a watch coming up to cover these. Or the Storm Prediction Center has started to issue a lot of more finer scale mesoscale discussions that update what's going on now. So if there's 1 or 2 storms that are really powerful, they kind of talk about why that might be, or maybe even that the storms haven't been performing as expected, but the atmosphere is still primed for it. So, hey, we're going to keep the watch in place. So you can see the progression here of the mesoscale discussions from SPC. They issued 3 on that day. The early one mentioning hail, because again, if any isolated storms develop, that was the main threat with the strong lapse rates. So we thought that was going to happen with some potential supercells. The later one to mention a cap was preventing those supercells from forming. So, okay, hey, maybe we aren't going to see any supercells, so the hail threat's going to be a little bit less. And then later on in the evening, after the squall line had formed, they mentioned, hey, the front is now moving through the area, and it's leading to a main wind threat with the line of storms. And then the SPC, the Storm Prediction Center, issues watches. So these watches are actually issued by the folks up in Norman, Oklahoma at the Storm Prediction Center, housed at the University of Oklahoma, but they are coordinated with us in the local office. So first, a mesoscale discussion comes out that kind of informs everybody, including the news media and the public who are paying attention, that, hey, a watch may be needed. But then SPC initiates a conference call. They'll call all of the offices in the potential impacted area and go, these are the counties that we want to put in the watch. This is the hazards that we want to put. We want to either do a severe thunderstorm watch or a tornado watch. Are y'all okay with that? And we'll go, yeah, that's fine. Or, hey, can you add these counties? Can you subtract these counties? Maybe hold off for a little bit. And then after we coordinate, SPC will then issue the watch. So because us as forecasters at our office on this day thought that the wind threat was the main hazard, we actually proposed to SPC that we side with a severe thunderstorm watch as opposed to a tornado watch. We thought that the tornado threat was a little bit less and that the wind threat was more, so we wanted to highlight that with the severe thunderstorm watch that was ultimately issued. Okay, so we're about halfway through this presentation, and it's time to start talking about radar. So now we've got storms going. We've got stuff already going on, and so now we're going to start stepping through radar and how we use that in an event to issue warnings. So what's on the screen now are basically the same view of storms across Kentucky through different apps. One's, I believe, called My Radar. One is called Weather Lab. You've got the National Weather Service webpage there, their mobile webpage, and then you've got Radar Scope. So, you know, which one's better, which one's worse? Well, they all kind of fit different needs. You know, some people may just want to know where the rain's at. So kind of a simpler radar app. Maybe one of the free ones out there is all you need. If you are a weather nerd and kind of want to do a lot more radar interrogation, then maybe one of the paid ones are a little bit better. But there are apps on your phone, on your computers, that you can either get for free or purchase to view all the radar data. But the important thing to remember is at the end of the day, all of the radar data still comes from the Weather Service. You know, it may be painted a little bit differently, it may be shown a little bit differently, but it's all the same data at the end of the day. So what is radar? Radar stands for radio detection and ranging. Radar is not just used in the Weather Service, but it's used in the military. It's used by cops to potentially give you a speeding ticket. You know, radar is used actually all around us. So it is, though, the most effective method of detecting precipitation remotely. So we've got 3 radars in our area. And again, it's looking at most of South Central Texas to remotely sense that precipitation. The technology has been around now for almost 70 years, from the early 1940s, and we have continued to improve that, again, through those last 70 to 80 years, through multiple renditions of weather radars, and we're still perfecting and adding to that technology today. It works by shooting electromagnetic energy in the form of microwave frequencies into the atmosphere. It's going to hit something like that blue water droplet there and then bounce back or reflected back to the radar, and that is where we get the term reflectivity. So it's basically the amount of scatter back to the radar is what you're seeing when you have reflectivity. So the radar starts at 0.5 degrees. It's the lowest scan that we look at, and then it starts to rotate and also scan upwards. So as it does so, you're looking at different layers in a thunderstorm. So here's kind of an idealized animation of what happens. Again, you're looking higher and higher in the storm, and that's what the coinciding radar images look like, all for one singular storm. So you notice as it gets higher, the precipitation is actually getting less because you're looking at the top now of the thunderstorm. We use also a lot of different scanning patterns, some called volume coverage patterns, basically how the radars operate and how many scans they do, but also things like what we call sails. And sails at the end of the day allows us to look more at the lowest elevation, at 0.5 degrees, a lot more often. So that's where a lot of our information comes from, because it's basically the radar image closest to the surface, what's actually happening at the surface there at the end of the day. So we want to look at that a lot. And so sails allows us to do that by scanning that first lowest scan, going up a couple more, and then actually dropping back down and looking at that lowest scan again. We also can do something similar with the middle area of the atmosphere. We call that MERL. We love acronyms in the Weather Service. And so this, again, does the same thing, but looks at the middle 3 layers, the middle 3 radar scans. And really what this is this benefits us because we can see a hail core dropping out of a thunderstorm. We can see a rotation potentially tightening up before it gets to the surface, because, again, it's got to be in that mesocyclone in the middle of the thunderstorm first before it's ever realized as a tornado at the surface. So, again, we use these different tools at the end of the day to view what's going on in storms a lot better. The other thing to consider is that the radar beam is not a laser. It's not a single point looking at it, but it actually spreads out as you get further and further away from the radar. So here's an idealized beam spreading where, you know, one storm may take up the whole entire radar beam, where the storm further away may only take up a portion of it. And by the time the radar beam gets 120 miles away, the beam itself is over 2 miles wide. The other thing it does besides spreading outward is actually spread upward, because you've got to think, as the radar beam goes out, the Earth is actually bending down and away from the radar beam itself. And also the beam is looking up more into the storms. So a storm closer to the radar, you may actually be looking at the lower parts, or right where, you know, all the precipitation is coming out. The storms, though, further away, you may actually be looking at the middle or the top of those storms. So these are all considerations us as radar operators and as meteorologists that we have to remember at the end of the day when we're using it. Also, there's something called the cone of silence. So you may have remembered that scene from the movie Twister, where they're out on the hill, Dorothy has just been knocked over, and they're all picking up those, you know, little sensors, and the tornado just disappears. And one of the guys who are following them whispers, "The cone of silence," like it's this, you know, moment of silence or something before the tornado comes back. Well, there's nothing like that in the real world, unfortunately, when it comes to tornadoes. So the cone of silence is actually that area above a radar that the radar can't see. So our radars don't ever point directly up. They do actually if we're doing maintenance, but in operations, they don't point directly up. So for us here in New Braunfels to see best what is actually going on over us, we have to use a neighboring radar like the one in Granger north of Austin to actually see what's going on in our area. So looking at what we call volumetric scanning, again, so that's looking at the whole volume, looking at all of those scans at one time. You know, you can put them together and look at pretty pictures like this from Weather Lab that shows a 3D rendition of the storms. And again, you notice as the beam goes up and away from the Corpus Christi radar, it's getting further and further from the ground. So once you get over to Houston and Galveston, you're looking only at the tops of those storms. Here is now a cross-section, again, of pretty much more radar data, and this shows fairly clearly that cone of silence. So again, you can actually see each radar scan as one kind of line going out from the radar, but then you don't see what's going on right above the radar, and that's that cone of silence because the radars don't point vertical. So Gibson Ridge, or GR Analyst 2, is a software that you can get on your computer, and one of the nice things it does is it puts all of those volumetric scans into a nice pretty picture, and you can get a 3D image of a thunderstorm. So that's what this is a 3D volume scan from the Granger radar of a Burnett County supercell that I believe ended up producing a tornado. So if you kind of strip back the 3D look, this is actually what that looks like. So again, these are each of the now individual volume scans looking up into the atmosphere. So again, still a 3D sort of representation, but now we're looking at the flat scans as opposed to it put together in a true 3D image. And then now looking at that more 2D, you can now see each of those slices now individually, from the base ones at the surface to the higher tilts aloft. And one of the things that you notice is that there are actually gaps in coverage aloft. So as you get, you know, basically above 5.2 degrees, you're now starting to get gaps in coverage where those scans below it actually overlap and provide more data. So this is where our computer systems, where these apps that are out there start to interpolate the data between these layers to produce the different images. Okay, so let's talk about radar coverage, okay? Because we've talked about, you know, distance from the radar and the data quality changes because you're looking at further in storms. And so let's start looking at those heights in a graphical representation. So anywhere shaded in blue here basically has radar coverage below 10,000 feet. So you see that's most of South Central Texas. Del Rio, Uvalde, Kerrville, Austin, San Antonio, they're all, you know, have coverage below 10,000 feet. And this actually is a larger map that shows all the way up to Midland, up to Waco, over to Houston, and then down to Corpus. So most of Texas actually has good coverage, although Laredo doesn't have coverage below 10,000 feet. We start to look a little bit lower. Now this is coverage below 6,000 feet, and you start to lose places like Schulenburg and Victoria, like the city of Llano, again, these radar beams are now looking over 6,000 feet in those areas. Looking at 4,000 feet, so looking, again, fairly close to the ground. Again, we've lost Llano, but places like Lake Buchanan, Fredericksburg, Kerrville, and then out to Bryan College Station, bigger cities like LaGrange and Smithville don't have coverage below 4,000 feet. So, again, the lower the coverage you can get, the more you know what's happening closer to the ground from these radars. So let's look at Austin and San Antonio and the effects of Earth curvature, and again, looking at that height. So here's an example of the Granger radar. This is the one located in Williamson County to the northeast of Austin. It's about 33 miles from downtown Austin. And so you're looking anywhere between 25,000 and about 10,000 feet above the ground. So that 0.5 degree scan is looking about 2,500 feet. So you're fairly close. If we're trying to observe a big thunderstorm going over Austin, we're going to be using that Granger radar. So now that radar in the center has changed to our New Braunfels radar, here basically located at the office. And now San Antonio is a lot closer, still about 33 miles away. And now the elevation that you're looking at over San Antonio is about 2,200 feet. So again, if we're looking at a storm over San Antonio, we're going to use our radar from New Braunfels. Now, with Austin and Georgetown further away from the New Braunfels radar, we're looking up higher in the atmosphere. So Austin to Georgetown is about 40 to 70 miles an hour away. And we're looking at now anywhere between 3,000 and 5,000 feet up. So we're looking more at the middle of thunderstorms, the middle of potential rotations, as opposed to closer to the surface. So we're going to be using different radars as we go to look at different features. Okay, so let's start talking about radar products itself. So some of these things, you're going to see in all these radar apps that we've been talking about. So reflectivity, velocity, spectrum width, differential reflectivity, correlation coefficient, and specific differential phase are probably the 6 most common products that you're going to run into looking at these different apps, or potentially see even used on TV. So this is what our computer systems look like in the office, and this is now a 9-panel that I have created at our office to look at radar. And so you can see a lot of those products that I just mentioned, in addition to others like echotops, like hydrometeor classification, where the radar actually tries to guess what is falling out of a thunderstorm. But here's a 9-panel, and I'm actually not looking at a thunderstorm. You may look at that top left panel and go, well, wait, what's that circular thing then with a bunch of red? Well, that's actually the Bracken Bat Cave. It is the largest colony of bats in the world that lives right on the Comal-Bexar County line in the Bracken Bat Cave. And a lot of the times in the summertime, they all come out in the evening to spend the night feeding on mosquitoes, thankfully, and other bugs. And so many of them come out because it's so close to our radar, about 17 nautical miles from our radar, that it actually looks like a small thunderstorm when it comes out. So it actually picks up 40 to 50 to 60 dBV, which typically we think is heavy rainfall. These are the different signatures that it picks up while it comes out. But, here's just one example of a radar feature that we're looking at. Looking at reflectivity, it's probably the most common one that you look at the end of the day. Almost every app out there has reflectivity. And you're measuring, again, the return power back to the radar from a target, whether that target be bats, whether that be heavy rainfall, hail, tornado debris, whatever that might be. It is the intensity of the target is inferred by how much power is returned. Obviously, if you're hitting something a lot more solid, it's going to return a lot more power. So that the hail, the heavier rainfall, those tend to show up as higher reflectivities, and the units are in dBc. But at the end of the day, like I just said, they don't always have to be meteorology targets. So this is actually Hurricane Harvey making landfall at Rockport. And as the rain bands approach South Central Texas, right there you can actually see a bunch of light reflectivity along I-35. That is actually all the bats in summertime coming out and getting caught up in those northeast winds along the periphery of the hurricane. So it's blowing all those Bracken Bat Caves, the Congress Avenue Bridge bats in Austin and others down to the southwest in those upper level winds. An important thing to remember is that all color scales are not created equal. So whether it's our internal systems, whether it's different academic web pages online, or even our web page online, or other people, they can adjust their own color scales. So always look back at that scale to see what the radar is actually correlating to. So here's an example from the DFW area of the same storms in two vastly different color scales, one more kind of green-based and one kind of more blue-based. So the intensity of the storms, again, is the same. And a lot of the times on social media or maybe on TV, these color scales are adjusted to make things look worse or look scarier. So a type of reflectivity is actually called composite reflectivity. And so it differs from the base reflectivity. Base reflectivity, how it works, is just the maximum reflectivity from each elevation scan. So looking maybe at that lowest level, or looking at the middle level if it's, you know, say the 5.2 degree scan or whatever. So you're looking at each level in the thunderstorm when you're looking at base reflectivity. Composite reflectivity takes all of those values and only returns the highest reflectivity value at any given point. So in this example, you have a thunderstorm with rain at the surface, lower reflectivity up in the thunderstorm, but at the mid-levels of the thunderstorm, you have hail, so it's going to return higher reflectivity. And so something like this may result. So on the left, you have, again, that base reflectivity at the surface, where composite reflectivity kind of blows up and makes things look a lot worse. And again, what you're actually seeing here is you're actually seeing the reflectivity aloft. You're seeing that elevated hail core in these two circled thunderstorms. And we use this a lot of the times to mainly just assess how severe the atmosphere is, see where the stronger storms might be. You lose features like lower level hooks that may indicate tornadoes, or other lower level features when you look at this composite reflectivity. But again, it just really quickly adds to our interrogation and our situational awareness, showing things like descending hail cores, like in this 3D reflectivity loop here. Okay, velocity, probably the second most common product that you're used to seeing. It measures the radial velocity of a target, which we'll talk about in a second, in knots. So when you look at an image like this, usually you're going to see a lot of reds and green. The reds and the warmer colors are winds actually blowing away from a radar, where the greens and the cooler colors are winds blowing towards the radar. So here's an example of the May 20th, 2018 Leander tornado. And as I already stated, when you have the green going towards the radar and the red going away from the radar right next to each other, that's indicative of rotation and a potential or actual tornado. Okay, so let's talk about one of the most common issues with velocity, and it's called side lobe contamination. And it basically has to do, at the end of the day, with the fact that the beam from the radar is spreading out, and it actually starts to collect erroneous data away from thunderstorms. So here's an image of a thunderstorm on the left and velocity on the right, and we got a call into the office saying there's a tornado northwest of Briggs, which is labeled there, just north of US Highway 183. So you're looking at that and you're going, okay, based on that last slide, we're looking for greens and reds next to each other, okay? I see two of those, one right near Watson and one kind of more off to the northwest near that label of US 183. Which one is real? So again, there's your two circulations. First, you've got to look at reflectivity. Up to the northwest, there's good reflectivity. It's kind of in the hook where you would expect a circulation to be. But near Watson, there's really not much reflectivity. And again, this is that erroneous data of the radar trying to interpret basically empty air, but erroneously doing that and putting false velocities there in those areas. The other thing to look at here is it's actually rotating the wrong direction for it to be a true tornado. So that's another hint that it's incorrect. But probably the biggest hint is to actually look aloft. When there's a good, strong tornado out there, you're going to have a rotation through the thunderstorm, not just at the lowest levels, but throughout the thunderstorm. So if we look at 1.3 degrees, just a little bit off the surface, that rotation to the northwest is still there, still alive and kicking, but now that thing near Watson is completely gone. So that's what we call side lobe contamination. So a lot of the times we'll get phone calls, we'll get comments of people going, oh my gosh, there's this big velocity couplet, where in actuality it's just actually side lobe contamination and actually erroneous data at the end of the day. So radial velocity explained. So how the radar tracks velocity is radar radial velocity is the component of the true velocity that is moving directly towards or away from a fixed point. So if the radar is directly in line with an object, you're going to actually get that directly indicated speed. So if it's right in line, it's going to be the object speed of 80 miles an hour, and the radar indicated is going to say 80 miles an hour. But a lot of the time it's like this, where the radar is actually slightly off kilter or off angle to whatever target is looking at, and you have to take into account that angle at the end of the day. So the object speed may be 80 miles an hour, but the radar is going to indicate 73 because of that angle. Another feature that we use, and this one really comes into play when we start examining tornadoes, is called storm relative velocity. So this actually subtracts the storm motion from the overall velocity, and in effect what it does is it gives us a representation of the wind motion if everything out there was stationary. So obviously we know that storms move in a direction maybe towards or away from a radar, but to see things like rotation in a storm, we need to subtract that storm motion from that to be able to look at the rotation. And it's also important to know where the radar is, especially when we're looking for these rotations. So this is an image of base velocity, and I want you to look kind of down near below, down in this area where I'm circling with the cursor. So you see a lot of bright greens, maybe a low area here, maybe some potential reds. But now when we subtract the motion of this line of storms here, things become a lot more obvious. So you now have the reds and the greens right next to each other, and that is actually indicative of a weak rotation in that area. So again, we use storm relative motion a lot, storm relative velocity a lot when it comes to looking for tornadoes. Another product, and I would say probably one of the least utilized products, but one that I have found very interesting in the last couple of years, is called spectrum width. This was actually one of the first three original radar products. It was reflectivity, velocity, and spectrum width were the very first three products before dual polarization was developed. And it's basically a measure of the turbulence in the atmosphere. So low spectrum width happens when air is moving in one direction. If there's a lot of turbulent air moving in different directions, you get a higher spectrum width. So this could indicate potentially a tornado, some type of rotation, or maybe convergence, air coming together. So in this case, you see right along the squall line, in the Boeing section of the squall line down to the south, you actually have a lot of higher spectrum width, showing a lot of turbulent wind. On the northern part of the line, where it's a lot more unidirectional wind coming out of the thunderstorms, you actually only get a thin line there where the convergence is happening right at the beginning of the thunderstorm. Okay, so let's talk about dual polarization, and specifically two different phenomena that we can actually see now that we have dual polarization, called a three-body scatter spike and a tornado debris signature. So dual polarization allows us to better distinguish between rain, snow, hail, bats, debris, basically whatever is falling out of the atmosphere, because we're now looking at both a horizontal and a vertical pulse from our radars, two pulses, not one. We can actually start to see shapes a lot better from the targets that the radar is seeing. So whether that's a small raindrop, whether that's a bigger hailstone, or maybe a weirdly shaped mosquito or bat, we can actually start seeing these features better now that we have dual polarization. And the two main products that we use are differential reflectivity, which is the difference between that X and Y, or that horizontal and vertical reflectivity factors, a good indicator of drop shape, and basically what is falling out of the atmosphere. Is it, a uniform shape like a drop might be, or a snowflake might be, or maybe it's ice crystals, more linear kind of thing, or maybe it's more oblong like some of our biological features might be. The other product is correlation coefficient, and this one now looks at the change in these horizontal and vertical characteristics over time. So the more scatter, the more change there is, the lower the CC is going to be, and this can be things like bugs, buildings, or bats that we've talked about several times, or tornado debris, which we'll talk about here in just a second. As you get towards higher correlation coefficient, that's more uniform. So things now start to get more like hail, or especially wind, driven rain or winter precipitation these more uniform shapes. So even if we have bats and rain in the same reflectivity image, I can switch over to correlation coefficient and actually start to see the differences because of the different shapes of these targets that the radar is hitting. So one of the uses of correlation coefficient is actually to look for three-body scatter spikes. So this is caused by large hail. Basically, the radar beam shoots out of the radar, finds a thunderstorm with large hail, but instead of being reflected right back to the radar beam is actually reflected down to the earth by the hailstones and back to the hailstones and then back to the radar. And that extra trip down to the surface of the earth creates this erroneous data out the back of these thunderstorms, and it ends up looking like a spike. And so when we see that, we know that there's a lot of large hail in the column of that thunderstorm that the radar beam is actually reflecting off of. So let's talk about a couple of local severe weather events, local hail events. So the costliest hailstorm storm in Texas history occurred back in 2016 as a big, massive thunderstorm went across the northern parts of San Antonio. So you can see the 3D representation of the hail core there and the 4 to 5 inch hail that fell out of it. But now we can actually look at that three-body scatter spike on radar. So you can see the spike on reflectivity, but because it's erroneous data, it's actually going to come up as very low correlation coefficient when we're looking at the dual pole variables. So this is, basically the radar guessing that there's a 100% chance of severe hail and estimating anywhere between 2 and 3.5 inches hail size from its algorithms based on the three-body scatter spike and other features. Again, we saw that it was really 4 to 5 inch hail, so the radar was underestimating here. But it's definitely enough information that we can put out a warning, alert people to it, and then try to start to guesstimate how much the size of the hail is. Here again is a kind of plain view look at it, a cross-section view. Again, and all of that is erroneous data, but it still provides that hint that there's a lot of hail going on. It's now the largest hailstone ever recorded in South Central Texas. Now back in 2018 from my neck of the woods in Bastrop County. You're going to see as these storms blow up right along I-10, one storm head to the east and one storm head to the northeast. It's that storm that heads to the northeast here that ends up producing the large hail very near Smithville, Texas. So here's some pictures of anywhere between 3.5 to as much as 5.5 to 6 inch hail that fell with this event. And here is the radar representation. So it may be a little bit harder to see because of that storm in the background, but you still have that lower correlation coefficient representing that three-body scatter spike. So again here, 100% chance of severe hail, which is hail of an inch or greater. Obviously, we got a lot bigger hail than that. And again, the radar estimates are anywhere between 2 to 3 inches of hail, underestimating again with this large hail. But again, the three-body scatter spike is really what we're looking at with the correlation coefficient and these other dual pole variables. The other thing that we look at is tornado debris signatures. So this is actually now the debris from a tornado being lofted up in the atmosphere, and because it's going to be boards and skateboards and pieces of cars and houses and sheet metal and all of these oblong-shaped things, because it's going to change so much, we're going to actually get a drop in correlation coefficient. And so seeing that drop in correlation coefficient tells us that, hey, there's debris being lofted in the air. And we can actually issue what's called a radar-confirmed tornado just based on this, because it's saying that, hey, that rotation that we're seeing is actually strong enough to produce a tornado because there's debris being lofted in the air. Okay, so with about 15 slides left, let's start looking at the radar from our January 10th event. So really in the 3 to 5 o'clock range, things have already gone linear. So some of these storms did end up producing some severe hail across Llano County. You actually do see a three-body scatter spike there just to the southwest of Fredericksburg. We didn't get any confirmed hail reports out of that storm. But again, just because there wasn't a spotter there to report it doesn't necessarily mean that there wasn't some severe hail falling out of it. But again, we've gone linear really quick. So even though there is a little bit of a severe hail threat here, we're already thinking wind threat and potentially some isolated tornadoes with that. Going just a little bit further in time, our first tornado warning of the night was at 5:23 up in Burnett County, and you can see that kind of more broad rotation there within the red tornado polygon that's happening just to the north of Burnett. Stepping even forward in time, our second tornado warning came out of a storm in Kendall County that also we thought was producing a hail of over 3 inches in diameter. So you can see the rotation there in the bottom 2 slides with the velocity and the storm relative velocity, but also the high reflectivity and the high maximum expected hail size out of the top 2 images. So that was a dual threat thunderstorm that we thought, again, still in the line here, but now more of a potential tornado threat. So this is that storm and animation of it. Again, as it kind of forms across central Kendall County, first looking at the hail threat, but then that rotation begins to wrap up and we issue a tornado warning off of that. Going on a little bit later, San Antonio was really impacted by these storms. The storms were a little bit weaker up in Austin's neck of the woods, but San Antonio definitely bore the brunt of these storms. We had multiple reports of anywhere between 60 and 80 mile-an-hour winds with this line of storms, and you can actually see those increased winds there in the velocity image on the right. Our third tornado warning actually came out of that Cibolo Shirts area that I showed you earlier in the presentation, and we did have other weaker areas of rotation, like the one north of San Marcos. In these linear events, these circulations can come and go very quickly. Again, not all of them always produce tornadoes, but they are there. We did have a tornado possible tag, and that's the thunderstorm warning there, but we didn't issue at the time a tornado warning with that. So let's look at this. This is now a couple minutes later, looking at base velocity. Again, this is now looking without subtracting the speed of the thunderstorms, and kind of look at it and see how many circulations you see along this line. And if you want to pause the video, feel free to kind of get your bearings and count. Now, if we subtract the speed of that line of storms again and look at storm relative velocity, how about now? So looking at it, there's at least 4 circulations here, one of which is warned, and there could actually be potentially 2 more south of this that you could have looked at. This one here and then this one here. So again, these are very small spin-ups that can occur along the line and may or may not be actually producing a tornado. So there are issues along the radial. So now where our New Braunfels radar is, notice that gray line that forms as the line of storms passes over. That's because, again, the storms are moving perpendicular to the radar beam and cause that gray line of velocity data there. And then one more weak circulation occurred just to the northeast of Smithville and actually moved into Fayette County to the east. We didn't have any confirmed tornadoes with this event. While we had several of these circulations, we did go out and survey several of them, which we'll talk about in the next slide, but we didn't ever get any confirmed tornadoes and just call basically everything very, very strong straight line wind damage. Okay, so to wrap up and kind of bring this back to why you, the spotter, is important. So post-event and really even during the event, we need reports from you. So things that we want reports are tornadoes, rotating wall clouds, and funnel clouds. Hail of any size, because even if it's nickel-sized hail and sub-severe hail, if we get that report from you and know that the storm is growing, then we can issue a warning for those folks down the line from you and help warn them of the impending threats. Wind damage, and then flooding or extreme rainfall amounts also. When you report to us, whether that be via Twitter, via a phone or a web report, we like 3 things: the time, the event, and the location. So is it happening now? Did it happen 30 minutes ago? What happened in as much detail as possible, and then a location. Typically, I mean, if you know Latin lawn, give us that. If you want to give us your address, we can pinpoint that. Or, just a common street intersection close by would honestly do well. But we do want as an exact location as possible so we can correlate that to different things that we're seeing on radar. Again, you can tweet us at #EWXSpotter. You can tag us in reports on Twitter and Facebook, and we'll get those that way. So really, again, as I said, for this event, we had to start to distinguish between wind versus tornado. So these are some of the damage reports that we got from across the area, and trampolines being thrown, some siding and other things being thrown at a car to damage it, and even some corrugated steel kind of barns and such being blown down. And so we kind of have to look at things and go, well, wait, which is it? And it can be hard to determine, and a lot of that has to do with the fact that, you know, we can get intense wind like we saw in San Antonio. We had measured winds of anywhere between 70 and 80 miles an hour, like at the Stinson Municipal Airport. Well, that range of wind is actually in that EF0 wind speed category, you know. So is it an EF0 tornado or is it straight line winds? And at the end of the day, even those two things can produce basically the same damage. So a lot of the times we'll get a phone call saying, oh my gosh, I got hit by a tornado, and we have to actually start looking at the damage to really determine that at the end of the day. And part of what we do is we look at things called damage indicators and the degrees of damage when we start to go out and correlate things to the enhanced Fujita scale, that scale that we use to rate tornadoes. So this is me back in 2014. On my phone, I'm manually entering data into an app that we have in the Weather Service that looks at these damage indicators and these degrees of damage to come up with a rating for this tornado, which happened to be an EF2. It only impacted this one house that you see in this picture, and I actually picked this house up very much like Wizard of Oz style, moved the house, a football field, with the family taking shelter inside, and put it back down. The family is fine. They were taking shelter in a bathroom like they should have been, in their bathtub, just a couple of scratches and bruises, but they were definitely there for a wild ride. So after all this occurs, we again will do either storm surveys by going out and looking at the damage or collecting pictures of the damage and analyzing that. And then we will put all of this out in what we call local storm reports. So any reports that you give us, if they were severe, we'll take them and put them in these local storm reports so that the media, so that researchers, so that everybody can actually see these reports from the event. So that's an event at the end of the day, going from all the way basically a week out, looking at the global weather models and the typical setup, to the changes and looking at the ingredients and what types of storms are going to form as we get into the event, and then obviously all the radar interpretation that goes on during events. And then the importance of you, the spotter, after the event and during the event to give us the reports that are actually falling from the storm, you know, in real time. So thank you for attending the Advanced SKYWARN. If you have any questions and, you know, need any assistance about anything, feel free to email me. My email is there on the screen, and I'm always happy to answer any questions about the weather, about what you have. If you're interested in becoming an official spotter for our county warning area, feel free to email me, and I will set you up with our warning coordination meteorologist and how to become an official spotter. But again, thank you for watching the training.